Assalamualaikum warahmatullahi wabarakatuh. We are from group RAS 2037B. Today we will present about our group assignment with the title Energy Harvesting, Turning Waste Heat into Electricity. Our group consists of 3 members. The first member is Nur Najah binti Hamzaki, second is Nur Nafisa binti Sulaiman, and the third is Aunit Riani binti Sanipur Aswadi. My name is Nur Najah binti Hamzaki. So before we talk about energy harvesting, it is important to understand the problem we are trying to solve, which is wasted energy. Globally, more than half of all the energy we produce does not get used for useful work. Instead, it is lost as waste heat and released into the environment. This means that for every unit of energy we generate, only a small portion actually becomes electricity, motion, or light that we can use. This waste heat comes from many everyday sources. In industrial settings, such as power plants and factories, large amounts of heat are lost through furnaces, boilers, and also hot pipes. In vehicles, internal combustion engines are highly inefficient, and most of the fuel energy is lost through engine heat and exhaust gases. Even electronics, laptops, smartphones, and data centers, electrical energy is constantly converted into heat during operation. The problem with waste heat is not only inefficiency, it also leads to high fuel consumption, increased operating costs, and greater carbon emissions. As energy demands continues to grow, wasting such a large amount of energy is no longer sustainable. Now that we understand the scale of the wasted energy, the next question is how we can convert the waste heat into electricity. This is made possible through a physical principle known as the thermoelectric effect. The thermoelectric effect allows heat to be converted directly into electrical energy without any moving parts. When there is a temperature difference across a thermoelectric effect material, with one side being hot and the other side being cool, charge carried inside the material will gain energy on the hot side and move toward the cool side. This movement of charge creates an electrical voltage. One of the most important aspects of this process is that it is very reliable and low maintenance. Because there are no moving mechanical components, thermoelectric systems can operate silently and for long periods without significant wear. As for the key material property that determines how effective this process is called the Seebeck coefficient. The Seebeck measures how much voltage is generated for a given temperature difference. Materials with a higher Seebeck can produce more electrical power from the same amount of heat.
Now that we understand the introduction of waste heat, I will explain the physics behind the solution. So, what is a heat engine? To analyze the thermoelectric generator or TEG, we must first view it through the lens of a heat engine. By formal definition, it is a thermodynamic device that operates in a cycle to convert heat into useful work. TEG fits this definition perfectly through 4 essential characteristics. Firstly, heat reception. It receives heat from a high temperature source, such as an EV battery or car exhaust. Secondly, conversion. It converts a portion of this heat into electrical work. Thirdly, heat rejection. Crucially, it must reject the remaining waste heat to a low temperature sink like the ambient air. Lastly, cyclic operation. It operates continuously, returning to its initial state to repeat the process. This leads us to the second law of thermodynamics and the Kelvin Planck statement. It reminds us that no device can be 100% efficient. We cannot convert all heat into work. Every heat engine must waste some energy to a low temperature reservoir to complete the cycle. In an electric vehicle EV, this is highly relevant. While EVs don't have traditional exhaust, the battery and power electronics get very hot during operation. By placing a TEG between these hot components and the cool outside air, we create a temperature gradient. The second law tells us that the larger this gradient, the more potential we have to harvest electricity, which directly extends the car's driving range. For a deeper insight, we look at the temperature entropy diagram. The goal is to move as close as possible to the theoretical Carnot efficiency, turning what was once waste into usable power. Next, Auni will take over to explain challenges and limitations and more that allow us to achieve this efficiency.
Assalamualaikum warahmatullahi wabarakatuh. My name is Auni Iriani and today I will presenting about challenges and limitation of energy harvesting. Although waste heat is widely available, converting it into electricity is not easy. The main challenge is low convention efficiency. Thermoelectric generators are limited by fundamental thermodynamic laws. So in real application, only 5 to 8% of the waste heat can be converted into electrical energy. Another challenge is high material cost. Efficient thermoelectric materials such as bitumen electrolyte perform well but are too expensive and not suitable for large-scale development. In addition, thermal management is critical. A temperature difference between the hot and cold side must be maintained. If the cold side heats up, the temperature gradient decreases and power generation drops. This limitation makes large-scale power generation is difficult. Despite this challenge, the future of waste heat energy harvesting is promising. One important direction is the integration with the Internet of Things, where the small thermoelectric devices can power sensors continuously without batteries. Research is also moving forward towards flexible and organic thermoelectric materials, which are lighter, cheaper, and more environmentally friendly than traditional materials. From the sustainability perspective, harvesting waste heat helps reduce energy loss and lowers carbon emission. Even though the power output is small, the large-scale adoption can contribute significantly to energy efficiency and environmental protection.
In conclusion, waste heat represents a significant but underutilized energy resources. Thermoelectric energy harvesting applies fundamental heat engine and thermodynamic principle to recover part of this lost energy. Although the efficiency is limited by entropy generation and material constraint, while it is not suited for large-scale power generation, continued material innovation and integration with IoT technologies make the waste heat recovery an important contributor to future sustainable energy system.